Today we are going to look at the function of tangent and how it relates to the sine function that we have previously looked at. In the viewing window that you currently see, we have graphed g of x is equal to sine x from negative 5 pi over 2 to positive 5 pi over 2 as far as the domain goes. I'd like to point out that we have vertical lines at negative 5 pi over 2, negative 3 pi over 2, negative 1 pi over 2, 1 pi over 2, 3 pi over 2, and 5 pi over 2. And note that these are odd numbered pi's over 2, both negative and positive. And as when we graph the tangent function, you're going to see that these vertical lines play a critical role in shaping the tangent. So let's go ahead and graph that function now. So we're going to go ahead and graph the tangent. And as you can see, those vertical lines create what we call asymptotes. In other words, they basically act as barriers against which the lines come up against but never touch. We've talked about asymptotes before. Note also that the tangent and sine functions intersect at the x-axis at intervals of pi. Negative 2 pi, negative pi, 0 pi, 1 pi, 2 pi, 3 pi, and so on. So whereas the sine and cosine have periods of 2 pi, tangent has a period of 1 pi. So those are some important properties or concepts to think about as we look at this tangent function. It should be pointed out that the domain of tangent are all reals except odd multiples of pi over 2. In other words, where the asymptotes are. Our range, in other words, our y values, are all the real numbers. It is symmetric with respect to the origin. Notice that it takes on some similarities in shape to a function that we've already looked at, y equals x cubed. In that, but unlike y equals x cubed, that is continuous or has a domain of all reals, these do have asymptotes at those points that points that we've pointed out with those red vertical lines. Okay. You should note that tangent, and I'm going to type this in here, that tangent tan x is equal to y over x, which is the same as sine x over cosine x. And it's interesting to note that whenever cosine x is 0, that the division now becomes undefined, and cosine x is 0 is where those asymptotes appear. So if you were to look at the cosine of negative 5 pi over 2, it would be 0. If you looked at the cosine of negative 3 pi over 2, it would be 0. And so forth. Every time you see an asymptote, the cosine of that x value is going to be 0. So that's important to note. Okay. In the equation, y equals, and let me type this out here too. In the equation, y equals a times tan, and then we have the b, and it's x minus h plus k. That these basically take on slightly different meanings than we've used with the than we had with the sine and cosine. Okay. First off, being that the constants a, b, h, and k, they influence the behavior of this function in much the same way that they do for the graphs of sine and cosine. The constant a gives us a vertical stretch or shrink. B still affects the period in that b is equal to 2 pi over the period. Okay. H causes a horizontal movement of left to right, same way as it does with a parabolic curve. So if I have x minus 5, that means I am moving that inflection point 5 units to the right. If I had x plus 3, I'd be moving the inflection point 3 units to the left. And k causes a vertical movement up and down. So if I were to have tangent x plus 3, I would be moving the inflection point 3 units up. Or if I had tan x minus 4, I would move the inflection point 4 units down. So just like the vertex is used to determine the location of a parabola, our inflection point, where the curve turns from curve up to curve down, or curve down to curve up, that inflection point is the position or the determining factor, the location of our tangent curve. Okay.